Thank you, Craig. Updating more traditional agricultural practices by making changes like those Craig described will be critical to future food systems, but technology is opening up opportunities to design food production systems that stray even further from the agricultural practices of the past. Here to tell us about how to make sustainable, year-round greenhouse crops work for all sectors of the food system is Neil Mattson. Neil is the Associate Professor and Greenhouse Extension Specialist in the School of Integrated Plant Science at Cornell. And Neil will be telling us about a systems approach is needed to catalyze a sustainable, year-round, locally grown produce industry in the Northeast. Thank you, Neil.
Thank you, Leslie. And good morning, everyone. It's a pleasure speaking after Craig. I grew up on a small farm in northern Minnesota that stayed and still is a 165-acre operation. So it's fun to talk about that integration from a farm perspective. So what I want to talk about today is production from the standpoint of what I term controlled environment agriculture. And Cornell has about a 25-year history studying this area. So essentially, there would be many areas that fall into controlled environment agriculture, but I'll talk about greenhouse hydroponic vegetable production. And the reason why we're interested in this area is if you look at consumption of fresh vegetables in New York State, most of them are coming from out of state. So New Yorkers consume about 12 pounds per capita of lettuce, and 93% of that comes from out of state, mainly from California and Arizona. Similar with spinach and strawberries. Tomatoes, about 18 pounds fresh. Many of those come from Florida as well. And also from greenhouses in Canada and Mexico. So if you look at the average food miles that those lettuce, spinach, and strawberries took to get to us in New York, tomatoes are on the low end with 2,000, but it's up to 2,700 to 2,900 with strawberries and lettuce. And despite the fact that we feel that there's this increased demand for locally grown food, and indeed, we have found that local food demand has increased from a $1 billion a year segment to a $7 billion a year segment just in the last 9 years. And that would include all of local food, including animal products as well. For one retailer example, Whole Foods has told us that their consumer demand and sales for locally grown has doubled since 2012. And to further validate that, the National Restaurant Association tells us that locally grown is their top produce trend for 2015. And so before my history at Cornell, which started as a collaboration between a horticulture professor, Bob Langhans, and an engineering professor, Lou Albright, they developed systems for growing hydroponic lettuce in a greenhouse. And they felt that was a way to overcome those, environmental variations that you have day to day. If you only grew lettuce outdoors, you could harvest it for maybe 5 months out of the year. And we wanted to develop a system where you could harvest it uniformly and repeatably year-round. So in the greenhouse environment, we heat to a common temperature every day of the year, and we also provide light or we shade so that all the plants get the same daily light integral every day of the year. And so that collaboration developed into the 6,400 square foot kind of small scale prototype of a commercial greenhouse. So this is Finger Lakes Fresh, about 3 miles from here. And you see the outside of it and then the inside of it where lettuce is produced in these hydroponic ponds. Through lots of systems development, looking at all areas of production, including fertilizers, respacing plants several times during production, a really high intensity of production could be achieved. So the 6,400 square foot facility produced over 1,200 heads of lettuce every day of the year. And on a per square foot basis, which is what we love to look at as scientists, 70 heads of bib lettuce per square foot per year. This has had some impact. We certainly see increased hydroponic lettuce production nationally, but it's still a fairly small segment of the produce industry. And in New York State, the USDA Census of Agriculture gives us stats that we can look at every 5 years, which I love to analyze. So that greenhouse vegetable segment has grown from 201 operations in 2007 to 435 in 2012. The wholesale value increased by 54% to $27 million. And we're the second ranked state nationally for greenhouse vegetable production. But as you can see, it's still a fairly small industry. And these stats for acres of greenhouse space in New York also include high tunnels or simple unheated greenhouses, which are great for season extension and they have low input costs. But again, you're only producing for so many months out of the year, and you can't produce in the winter season. So then you might wonder, why isn't there more controlled environment agriculture in New York State? And there's probably lots of reasons, which is why we need to talk about the systems approach so that we can address all of those different reasons. But four that I was able to think up of, and you'll think up of other ones, are securing financing for a capital-intensive business. So to construct a greenhouse, a nice high-tech one, it costs about $50 per square foot. And to operate that greenhouse is maybe another $10 or $12 per square foot per year for energy and labor. We also have issues related to the availability of skilled and unskilled labor, just like much of agriculture has those same issues. There's also increased need for processing and a marketing infrastructure, what we're now calling food hubs, could really be used by this CEA industry as well. One example of that would be increasing regulations that operations face related to food safety. And to follow those food safety regulations, it's much more cost effective to do that in kind of a cooperative way where several producers work with one processor that can meet those regulations. And then, as I mentioned, we need a lot of light in greenhouse production. So electricity is fairly expensive in New York State compared to some other parts of the country or compared to, say, Canada, which has a lot of hydroelectric. And talking about a systems approach, our group has thought about that for the last 25 years, and I don't expect you to read all of this, but this was the integrated system that Lou Albright thought of for greenhouse production. So everything from on the top left corner is defining what is a suitable site for CEA. On the top right, then the production requirements for growing lettuce seedlings. On the bottom right, for further growing those plants until they're harvested. And then the growing environment as well. And optimizing and controlling that growing environment has been a large focus of the Cornell Controlled Environment Agriculture group. So why have we focused on light and temperature? So light is key for year-round production, and I love this graph. All of these little dots are 1 day out of the 14 years from 1983 to 1996, and it's the daily light integral, so the total amount of light that we got outside. And then the greenhouse cuts light transmission down about 30% as well. So if you want to have uniform, consistent, reproducible plant production every day of the year, you have to take this light variable, which fluctuates really dramatically, and you have to stabilize that to that yellow bar, which shows you what optimum daily light integral is for lettuce. And so if we don't add supplemental light, it doesn't cost anything to light, right? But our production cycle also takes 3 times longer in winter. So it takes 105 days from seed to harvestable head of lettuce. If we add light to that target, 17 moles of light per day, we have 35 days from seed to harvest. However, it costs us $6 per year per square foot to light. And related to this light energy, we look at the carbon footprint, and we'll take lettuce as an example. So lettuce that's transported to New York, 2,900 miles. It's actually grown very cost effectively in California and Arizona in its outdoors in fields. And the largest factor that affects its carbon footprint would be the transportation from California to New York. We've calculated that ends up being 0.7 pounds of carbon dioxide per pound of lettuce. If we compare that to locally grown inside of a greenhouse, which we're intensively managing with heat and with electricity, it actually takes 2 pounds of carbon dioxide per pound of lettuce. So it's more expensive from a carbon footprint standpoint. So we can still value local food, but we have to be willing to pay a higher carbon footprint. So it's somewhat of a luxury item, right? So having fresh tomatoes and fresh lettuce in winter, whether you're getting it from California or getting it from New York, is a luxury item. If we don't want to eat these luxury items, we'll have to eat root vegetables, or we'll have to can and process all of our tomatoes in the summertime so that we can enjoy them in the winter. This light and energy in the greenhouse has been a real focus of our group through a collaborative research with Rensselaer Polytechnic Institute, where they have some of the nation's best lighting engineers. We're working on a consortium we call the Greenhouse Lighting and Systems Engineering, or GLAZE Consortium, and we're looking at lighting advances that we can make. And so LED lights are becoming more energy efficient than our greenhouse lights that we've conventionally used, high-pressure sodium lights. And we think these are the advances that can be made, and these are what the RPI engineers tell us. It's not going to be easy to make all of them. So this 50% improvement in LED diode efficiency is going to take several years, maybe decades to achieve, but we can get there. Better thermal management and optics, so directing light where we need it in the greenhouse and having less wasting and spillage of light, that we can achieve fairly readily. So that's 15% improvements. And our group has found that adding carbon dioxide, which plants need for photosynthesis, to the greenhouse environment can reduce the need for supplemental light by 50%. And we already have the technology to do that. We just need to demonstrate that on a larger scale and get that adopted by the industry. So if you multiply all those efficiencies together, we could reduce the cost of lighting to be only 21% of the original cost. And if we apply that to this carbon footprint, we can reduce local lettuce production in CEA to be less than the carbon footprint of producing in California and transporting to New York. Another example of how a systems approach might be taken to make CEA production in New York State more viable from both a financial standpoint and the carbon footprint standpoint would be coupling dairy manure anaerobic digesters with commercial greenhouses. And this is work that was done by Kurt Gooch and Tim Shelford of Cornell Pro Dairy. And so you see a picture of a dairy operation connected to an anaerobic digester to process the solid waste from that facility. From cows, we get an enormous amount of methane biogas daily that can be used then for generating electricity, as well as there's a lot of waste heat provided by that, and greenhouses have this large need for that heat. And so Tim Shelford has done these calculations for me that if we had a dairy with 850 milking cows, it could provide enough waste heat to heat that Finger Lakes Fresh facility, that 6,400 square foot facility. If we take the 600,000 dairy cows that we have in New York State, and we could get anaerobic digesters on all of them, which would be very difficult because many dairy farms are small, say 100 head of animals. But thinking large and globally, if we could use the solid waste from all of those dairy cows in New York State, we could heat 100 acres of greenhouses, and then applying those same productivity measures that I talked about, I've calculated we can produce 100 million pounds of lettuce per year, which would provide 42% of New York's lettuce demand. So just wanted to give you an example of how we can do what Craig was talking about, combining waste from one operation and using that as a valuable production input for another operation, and use that to make a more robust and reliable agriculture sector in New York State. Thank you very much.
Thanks to each of you. I personally found it fascinating and realized at the end we hadn't taken time for any questions. So at this point, questions for Nick, Craig, Neil. I hope that we do have a couple of microphones. So
question for Neil.
Neil Pullman. Fantastic job. Great presentation. So my question, you presented the data on the carbon footprint, products in California. How does the productivity compare? Typically, multiple harvests that you get in California or Arizona, overall productivity and cost, apart from the carbon.
Yes, excellent question. I don't know that I've calculated the cost per se, but when we look at productivity, depending on the field situation, we can produce, say, 10 times more per square foot in a greenhouse environment. So in California, you're maybe getting 4, 5, 6 crops out of that same land. We're getting, say, 20 crops or so in that same land. From a cost perspective, greenhouse production is very capital intensive, and so I would say that the cost is likely lower in California. From the back.
Have you looked for greenhouse innovation? Have you looked toward Holland for innovation? They have a lot of greenhouses and a lot of innovation.
Yeah, so the question was, have we looked to Holland and all of the innovations there? Very much so. I think of the Netherlands as kind of the world leaders in greenhouse technology. And I was just at a conference last week with a speaker from the Netherlands, and what they call kind of the next generation of greenhouses start adopting many of these changes that we're talking about. And they have similar thoughts that they can save about 50% of energy by integrating several different technologies that they already have. That it just takes capital to get those implemented. Yes.
3.5 decades ago, my senior project was to design a digester to generate electricity in our farm. How far has that really come? Is that a realistic reality today? What percentage of electricity, let's say, the farm was created in that process, and what's the future for it?
Yeah, and I'm not an expert in anaerobic digestion. I wish my colleagues Kurt and Tim were here. But they tell me that in the country there are only 85 dairy operations with really optimized anaerobic digesters producing electricity. So it's still fairly new and cutting edge. And I think it is expensive to implement them. And one of the things that Kurt and Tim are trying to demonstrate is that connecting it with an industry that has a tremendous need for heat and electricity goes a long ways toward optimizing the economics of it. So instead of selling your electricity to the grid for, say, 3 cents per kilowatt hour, a greenhouse operation would be paying 12 cents per kilowatt hour. So maybe you can split the difference with the operator of the greenhouse, and they get cheaper electricity, and you get a higher price for it. In the back?
No, I was just going to comment, like the Andrew Amplified. So it sounds like a new technology here. Europe is flooded with biogas digesters because they're paying 25 to 27 cents per kilowatt to be green, right? So the technology itself is plug and play anymore and incredibly efficient stage units. Yeah, but the current leader, yeah, we pay wholesale prices like 50 for this.
Maybe I can turn it. Is there a question?
Yeah, I have another question for you. You mentioned that we compared the carbon footprint, imported lettuce to locally grown greenhouse lettuce. And you said the alternative might be processing, freezing. We could grow lettuce here in New York and then freeze it.
Right.
What would the carbon footprint be for that? Say that we had to keep it cold for 9 or 10 months out of the year, frozen.
Yeah, and I haven't done those calculations, but one of our engineers has looked at the energy cost per acre of like a warehouse freezer versus a greenhouse, and a warehouse freezer has quite a bit lower, maybe 5 times lower energy cost than a greenhouse because it's well insulated, and so I think the economics do come out, and you can pack a lot of produce into there. I don't think I would want to eat frozen lettuce, though. Not even frozen spinach.
I have a question for Nick. I was wondering,
So I think it's really interesting using the spatial data to manage one crop that you have. But do you know any examples of people using the spatial data to decide what crops are appropriate to plant in a place, or making larger, broader land use decisions that way?
Oh, yeah. There's tons of examples. Tons of examples. So we also use, so just in our business alone, we use that, use spatial data integration to determine where we should purchase our next vineyard property, depending on some very specific food quality criteria. Can we produce grains appropriate for a $50 bottle of wine from this site? And so we have a lot of algorithms that we use to determine that. Here in New York State and also in Virginia, there's a great algorithm developed by NASA that actually analyzes areas of the Finger Lake based on the topography, their air drainage patterns, and determines whether or not, Vitis vinifera, the European wine grape, can grow on those sites. And just reviewed a paper last night from Virginia using NASA platform to do that. So, and it's across all the commodities, very, very similar things. Particularly in the horticultural commodities where you have these climatic limitations to high-quality production, there's increasing interest in application uses, but many people.
Well, we have a question for you. In planning the water management, soil, are you able to take into account the use of the soil to absorb the water?
Yes, we do that. So one of the, I showed when we run our soil sensors across the surface of the soil, I showed you one output of that analysis, but there's about 7 or 8 dozen different variables that we get from that, and one of them definitely is, there are several related to physical properties of the soil. They calculate the water penetration rate. And so we link that with our application rate to make sure that we don't exceed the amount of water that can enter the soil. So that is integrated back to the original purpose. That is integrated into the system.
So is that a proprietary software for the company?
No. We have it proprietary, but the same platform is available. There's a company called, I'm trying to think what I know it's SIS, I don't know exactly what it stands for. It's acquired by Trimble. And so probably if you just search that, they have electromagnetic sensors that they provide as a vendor service. They'll come out and map your soil, whether it's a vineyard, whatever, and they'll map your soil and give you these same kinds of data, for sure. Because we're so large, we have an economy of scale, we do it internally ourselves because it's just more economical that way. We invest in the technology. And also, we develop specific algorithms for vineyards that may be a little bit different than what they use, but no, it is available. There are several vendors that provide similar kinds.
How much have you analyzed how much has been the improvement in waste control from doing all these analysis?
I apologize, what control?
Wastage of your products, and you reduce the
Waste of our product. Well, to be totally honest with you, there's essentially in our system, again, I think because of our large economy of scale, there's essentially no direct waste. So, we take the juice. What's left over from winemaking are the seeds and the skin. So we have an analogous, we have a kind of an auxiliary business. We make in grape seeds are very, very high. This audience will appreciate this. There's very, very high levels of monomeric polyphenols, which are very good for you in a variety of different ways for cardiovascular health and other things. And so we make our seeds, we grind up and we extract the monomers, and so that goes into a product we know as activin, but it's sold by a variety of folks to convert for health purposes, nutraceutical purposes, and it's in a lot of different things, cosmetics and other things. That takes care of the seeds. And the skins, we wash them and take the sugar, any remaining sugar out of the skins, and then we send them to cattle feed. So essentially, within that, we have very, very little waste. All the excess of, say, wine that we have goes to the distilling material, we make brandy out of it, so it's a pretty close, tight system. And what really, our big challenge is water. And so we've gone from using about 4 gallons of water per gallon to make 1 gallon of wine. We're down now to about 2.5 gallons of water. We want to be 1 to 1 by the end of the decade. So we're working hard for it. Yes.
Hi, Nick. Can you speak to the challenges of, yield is very easy to measure and put it on a spatial basis, but can you speak to the challenges of managing quality and measuring it, and how possible it is to do that in real time?
Okay. Well, Tim, you hit my Achilles heel here. So here's the truth of the story. The metrics we use for quality are integrated aroma. We have the world's expert in aroma chemistry and grapes and wine, Gavin Mattson, somebody actually one of the people who probably posted with the Gallo, and appreciate Gavin's contribution. So we measure aroma compounds in the grapes, and we measure color and mouthfeel compounds in the grapes. And you copy. So the maps that I showed, these real time, we do have a multiplex sensor and a couple other sensors that we put on our harvesters that measure the grapes as they go across the belt real time. We have indirectly backed into the correlation of mouthfeel and aroma, mouthfeel compounds in particular. Aroma's much more indirect and just not so accurate. But at least for color and mouthfeel compounds, we've developed relationships between what the IR sensor is telling us and the composition of the fruit. And we've done that just painstakingly by collecting literally thousands of samples over time, correlating it with we've used, non-targeted analysis to match the signal that, relay signal with compositional analysis. We're working on aroma. Gavin's working on a project now to help increase the speed of our analysis, but it's not quite real time yet. So it's a good question. We can talk about it.
Question for Fred, actually. So you went from one product to 7, pretty much. From the cows to 7. There's a lot of risk into going into better purification, and I'm sure that over 20 years you've had some success with some natural good products as well. Can you comment about how you managed the risk and how you ended up with going forward and getting to the optimization?
Yes, and you're right that it's pretty easy to have sit to the start. One quick story was we were growing processing tomatoes back in 1992, and California produces 80% of processing tomatoes in the world, I think. But there was one small processor in Pennsylvania, and we were growing 60 or 70 acres of tomatoes for the processor. And we read about the California drought. And I said, oh, well, it's too bad for them, but maybe it'll help the tomato market. So we expanded our tomato production from 60 or 70 acres of processing tomatoes to 120 acres of processing. And during that great California drought of '92, and the price of processing tomatoes went from $120 a ton to about $80 a ton. And I remember that California had the largest processing tomato crop in the history of the state in 1992, up to that point. And the lesson I learned, and we heard it earlier, that you push one button and something had unintended consequences. Well, when California farmers were prorated on the irrigation allotment, they decided not to produce as much corn and field crops, and they produced more tomatoes and more intensely managed them. And that was a lesson for me. We were then out of the tomato business. We lost a ton of them. And I thought it was noteworthy that 2 weeks ago in the Wall Street Journal, we've heard about this California drought. This year, California broke the record for tons of processing tomatoes. So what happened in '92 has come back and happened again. The risks of, when you're doing one product, one commodity, you can become an expert. And I have lots of neighbors that have done that, and are very successful. They milk 1,000 cows, and that's what they do. We have taken a different path, and there is some risk mitigation by diversity, but there's always risks with new enterprises, and we found it challenging and at times. That answers your question.
Thank you. One question for you. I have to ask you. Field use and requirement also comes through, and they say that the harm that people have. So do you use hormones, or do you have another technique for it to use?
So our peg in the supply chain for milk is very narrow. We produce dairy replacements. Calves from the time they're born, and we breed them, and when they are ready to drop a calf and become a lactating cow, that's when we return them to the milking farms. So we do not use hormones, and there's a real effort now to reduce even the amount of antibiotics used in livestock production. I think California has passed new legislation on that. It's an important issue that's being discussed right now to get antibiotics out of the healthy livestock.
We're going to go ahead and move on. But, well, part of our